In this part, I will show you on how you can use the Hebbian training algorithm to learn a simple neural network architectures. So by learning means that the algorithm will predict the optimal value of W1, W2, bias, and also in terms of the value of theta. So basically from this particular question, so we given a 4 set of samples, which is in this case the all samples. So for the all samples means that 1 1 equal to 1, this is x1 x2, 1 0 will be 1, 0 1 will be 1, and then 0 0 will be 0. So basically for this particular problem, for the Hebbian algorithms, the Hebbian algorithm, the first step is to random the initial weight, means that we will give the initial value of W1, W2 and bias accordingly. And then later on the second part will be y equal to t. So in this particular case, y is actually the output from the neuron, whereas the t is actually the target that we set in the samples. So the adaptation of weight for this particular algorithm is that W new will be equal to W old plus n x I y. So for this particular case, n is actually the learning rate, in which for this case we set as the 0.5, and then x is the input. So we have two input here, x1 and x2, and then y is the output for that particular every particular sample condition. So the same thing with the bias. So for the bias, b new equal to b old plus ny, it will more or less the same with the weight equation. For this particular case only, we don't have any x. Because of what? Because of the value of bias input is equal to 1. So let's get started training this particular algorithm. So basically for the first step, we give some sort of the random initial value. So in this case, W1 equal to 0, W2 equal to 0, and then bias equal to -1. So what we can do is that first thing first is that we just need to fill up all the input to this particular table. So for this case, x1 is 1 1, and then our target is equal to 1. So the same thing for the second one, 1 0, the target will be 1. So for the third one will be 0 1, target will be 1, and then the fourth one will be 0 0, and also the target is equal to 0. So the next part, we go to the first algorithm. So the first algorithm stated that y will be equal to t. So means that this is our y. So y will be equal to t. So we just need to replicate all the value of t into the y. So the next part, we start doing the training session. So for this case, w new here will be equal to w old, which is the previous one that we have initialized early, plus n x I y. So in this case, x will be value of here, and then y will be value of here. So I will show you the step. So perhaps I'm using the different type of color. Okay, now for the first part, let's say I put this thing as number 1. So for the number 1 here, let me draw that thing here. So w new equal to w old plus n will be equal to 0.5, and then x y. So if I go to the first part here, so in this case, our w old will be equal to 0, which is the previous weight. Okay, so remember, we are interested to find what is the adaptation of weight in here. So the w old equal to 0, so plus 0.5. So the x for this part, since this is w1, so it's supposed to be directly related to the x1. So in this case, x is equal to 1, and then y will be equal to 1. So in this particular case, the value of the w1 will be equal to 0.5. So let's move on to the second part, which is the w2 part. So for the w2 part, so the same thing. So w old I just put this value here. Okay, so for the second part, which is the iteration number 1, so W2 of the old one will be equal to 0 plus 0.5, and then n will be x for the second part will be equal to 1, and then y will be same, which is equal to 1. So for this particular case, the value here also will be equal to 0.5. So the next part, we go to the bias adaptation. So for the bias adaptation, bn equal to b old plus ny. So this part, b old will be equal to -1 plus 0.5 of the adaptation, and then later on y will be equal to 1. So for this particular case, -1 plus 0.5 will be equal to -0.5. So we are settled with the first iteration of the algorithm. So now let's move on to the next part of the training. We go to the second iteration. So for the second iteration, we are in here, the second part. So for this particular case, so the same thing, we go w new here will be equal to the previous one. So I take this part. Previous one will be w old will be 0.5 plus n will be 0.5, and then for this part, the x1 will be equal to 1, and then y will be equal to 1. So for this particular case, 0.5 plus 0.5 times 1 times 1, so will be equal to 1. Okay, so now we move to the next part, which is in this case the w2. This part w2 will be taking to the x2. So in this case, if you look at this particular value here, x will be equal to 0. So if we use the same algorithm here, so means that if x equal to 0, so means that our w new equal to w old straight away, because of x or y, if it is equal to 0, your w new will be straight away equal to w old. So for this particular case, since x2 equal to 0, so we can say the w2 will be the same with the previous value of weight. So the next part, we go to the bias adaptation. So for the bias adaptation, the value will be -0.5 plus n will be 0.5, and then y will be 1. So for this particular case, -0.5 plus 0.5, so the value will be 0. So we are settled in terms of the second iteration for this particular case. So the next part, we go to the third iteration. So for the third iteration, you can see from here, x1, x2 is actually 0, 1. So since, as I mentioned previously, since x1 here will be equal to 0, so we can say the new weight will be equal to the previous weight. In this case, it is actually equal to 1. So we move on to the x2. So x2 here is actually the previous one. For the x2 here is 0.5 previous weight plus the learning rate will be 0.5, and then x will be 1, and then y also will be 1. So in this case, 0.5 plus 0.5 will be equal to 1. So the next part, we go to the bias adaptation here. So for the bias adaptation, the previous one is 0. Previous one is 0, and then plus 0.5, and then the value of y will be 1. So in here will be 0.5. And then finally, we go to the final part, which is the iteration number 4. So for the iteration number 4, the value is 0, 0 for x1 and x2, and also the y. So what we can say for the w1, since the x1 value is equal to 0, so the new weight will be equal to the previous weight, which is equal to 1. So the same thing with the w2. So for the w2, since x2 equal to 0, so the new weight adaptation will also equal to 1. And then finally, for the bias, if you look at this particular equation, if y equal to 0, so means that our new bias will be equal to the previous bias. So in this case, our b new equal to b old, because of what? Because of y is equal to 0. So we can say from this particular case, our bias is equal to 0.5, the new bias. So now we are up until this particular part of the equation. So once you are finished on the training all the data, so this is what we can say is that you have fit one epoch of the data set. So let's look at how we can utilize this information. I drag this upward a bit. Okay. So now currently we have the value of 1, 1 and 0.5, which is this is the value of weight after we perform the training session. So if we fed the value of the weight into our neuron, so we can say from here this is x1, x2, and then this is our bias, this is summation of weight, and this is the y. So for this case, our theta, which is the threshold here, will be equal to 1. So I just put here our theta equal to 1 straight away. So our first bias, our first weight will be equal to 0.5. This is the value of W1. And then weight 2 will be equal to 0.5 also. And then the third part in terms of, So let me draw a new one. Okay, from this particular neuron, I just draw back x1, x2, and also the value of 1. So this is the summation, and then theta will be equal to 1, which is this is the y. So for this particular case, our first weight will be equal to 1, just pick up here. And then our second weight also equal to 1, w1 equal to 1, w2 will be equal to 1. And then finally, the bias will be equal to 0.5. So we have this thing, we say this is the training, the value, optimal value after the first epoch of the training session. So what we can do is that we can actually calculate the accuracy of this particular value. So we just take our sample back, and then this is the predicted output. So let's say I put this thing as the y prime. So let's say in this case, this is x1, this is x2, and then this will be the target, and then this is the y predicted. So in this case, I just feedback 1, 1, 1, 0, 0, 1, and then 0, 0, which is the target will be 1, 1, 1, 0. So we want to estimate what is whether the accuracy, what is the accuracy for this particular value. So in this case, if we fed 1, 1 here, you just fed input value of x1 equal to 1, x2 equal to 1. So this is 1, 1. So 1 times 1 is 1. So 1 plus 1 plus 0.5. So the value here will be 2.5. So 2.5 will be greater than 1. So for this particular case, y prime will be equal to 1. So the next part, we try with the second part, which is 1, 0. So for the 1, 0 case, so if you fed the value, this thing will be 1, this thing will be 0, and then the bias will be 0.5. So which means the value for the second part will be 1.5. Sorry, I put here 1.5. So 1.5 is greater than 1. So for this particular case, it will be switch on, it will be fire. So the next part will be 0, 1. So 0, 1 will be more or less the same. So this thing will be 0, this thing will be 1, and this part will be 0.5. So we have the same value of 1.5. So 1.5 is actually higher than 1. So for this particular case, your y prime will be equal to 1, which will be triggered. So the final part, we fed the 0, 0. So 0, 0 means here that we fed 0, 0 here. So this is 0. The second part will be 0. So the third one will be 0.5. So 0.5 is definitely lower than 1. So for this particular case, we say that in this condition the neuron will not fire, so which is the value will be 0. So if we compare the value here, so this thing will be correct, y prime equal to the target in terms of the sample. The same thing with the second sample is correct, third sample also correct, and then the final sample also correct. So for this particular case, we can say that we gain the 100% performance in terms of the this particular weight value. So we just select this is our optimal value of weight that can be used in order to solve our sample that we fit here. So in the next part, I will show you how you can construct the decision boundary based on the obtained optimal sample. So for this particular case, if I plot back all the scatter plot here, so let's say this is our x1, this is our x2, so this is 1 and then this is 1. So let's say x1, x2, 1. So 1 I just put as a cross, and then 1 0, x1 is 1 and then x2 is 0, this is another one, and then the third thing is 0 1, which is this is the third location, and then 0 I just put different color here, so 0 will be another sample here. So this is our scatter plot of the sample. So let's say we have defined based from our training that the weight W1 will be equal to 1, W2 will be equal to 1, and also our theta will be equal to 1, and then the bias will be equal to 0.5. that able to solve this particular problem. So let's say you have been asked to draw the decision boundary based on this optimal weight into your scatter plot here. So means that you can estimate the predicted decision boundary will be somewhere in here, but how we can draw that thing on the scatter plot. So to do that thing, so let's look at our general equation for this particular neuron case. So for this particular neuron case, the general equation will be x1 w1 plus x2 w2 and then plus b. So in this case it can be with some condition, either is higher or lower with respect to the theta. So this is our general equation that we use in order to test the performance of our neuron. So if we wish to plot this decision boundary in your scatter plot, so means that first thing first, you need to feed all the value here into the general equation. So for this case, x1 w1 will be equal to 1 plus x2 w2 will be equal to 1, and then plus our bias 0.5. So in this case let's say higher or equal to theta will be equal to 1. So once we plug in all the values, so we are left with the some general equation of x1 plus x2 plus 0.5 higher equal to 1. So once we have this particular equation, so this part of this equation will be some sort of the relation. It will be higher or lower that will be used in order to threshold our model. But basically, if you want to develop your own equation, the function of equation, the decision boundary, so for this case we need to use to transform the relation here into equality. So what will happen for this case, we have the x1 plus x2 plus 0.5 will be equal to 1. So once we transform that thing, so in general this equation we can rearrange into y equal to mx plus c, in which for this case y will be x1 and then x2 will be x. So if we arrange that thing, so x1 will be equal to negative x2. I just move that thing to the right side, and then the value will be plus 0.5. So this will be our decision boundary equation. So let's try to plot this thing onto our scatter plot. So if we look at this particular equation, if x2 equal to 0, then xy will be equal to 0.5, which is 0.5 is somewhere in here. So the same thing, if x1 will be equal to 0, this is part will be 0. So x2 will be equal to 0.5, which is somewhere in here, because this is 1, this is 1, so halfway is somewhere here. So once we construct that thing, so in general we can draw our decision boundary. So means that for this particular case, this is the location or the illustration of our decision boundary. So for this particular case, our decision boundary equation will be equal to x1 equal to negative x2 plus 0.5. So this is the flow on how first you based on the given sample set problem. So we construct we iteratively find the optimal value of weight. So after the 4th iterations, so we test the performance of the system, which is in this case we gain the 100% performance. But in case your performance is not 100%, you need to repeat back the process. Means that the value of 110.5 will be on top of here, and then you repeat the process. After you finish the second approach for that particular case, then you test again in terms of your performance. If your performance is 100%, then you can stop the training. And then once you stop the training, what you can do is that you can plot the decision boundary on top of the scatter plot analysis. So that's the first part of our iterative simple neuron training algorithm, which is based on the Hebbian. Thank you.